Hello everyone, welcome back to another lecture in our episode on electromagnetics. And especially in the last class, we have started a problem solving, and especially we have done the problem of determining the electrostatic energy of a system of discrete point charges. So, in continuation, we will also look into another problem which gives you some emphasis on important concept on the nature of the electric field. So, what is the nature of the electric field is that similar to the case of the gravitational field, the electrostatic field is also conservative. So that means in the case of the mechanics, because you already studied mechanics in the last semester, and from that you know that gravitational field is conservative. And so is true for the case of the electric field. And we are going to explore this property in order to solve some problem. So that's exactly what we are going to do now. So we will consider an example problem now. So the statement of the problem is like this. So there is a charge plus q. So we will consider plus q for our analysis. The magnitude of the charge, I mean how many coulombs you are taking or how many millicoulombs you are taking, that's not important. So there is a positive charge that is present at some particular point, and let us consider that the location of the charge is r equal to 0. So r equal to 0 is something like considering it as an origin. You take any coordinate system and then you say that it is located at origin. That is what it means. So r equal to 0 need not be given. So I am just telling that we can consider that the location of the charge plus q can be taken as r equal to 0. So this will not be given in the question. There is a charge plus q, that's all. Okay, the location you have to determine by choosing an appropriate coordinate system. And most probably we are going to fix it at the origin, and therefore I am saying that r equal to 0 would be a good choice. Okay, so charge is present. So what is the question actually? The question is like this. Suppose if you are going to take 2 points, so let us say that this is a point here, and let us say that this is the point P1, and then let us consider another point here, for example, here. Let me put this particular point as P2. So there is a P1 and a P2. And then that's all. So the P1 and the P2 is not charge. P1 and P2 is just a geometrical point. It is just a location in the three-dimensional Euclidean space. Okay. If you want, you can consider them as x1, comma, y1, comma, is at 1. So there can be a comma here. And similarly, P2 is the second point, like x2, comma, y2, comma, is at 2. So these are the 2 points. And here r equal to 0 means we can say that this is x equal to 0, y equal to 0, z equal to 0. That's all. So what is the statement of the problem is, or what is that we are supposed to evaluate according to the statement of the problem is that evaluate the line integral E dot dl. So that is the question. So let me write down here. The question is this: evaluate the line integral electric field dot dl. dl is the line joining the 2 points, or how are you going to travel, that will be provided in the question. And we say that this is along a line. So I'll write down that this is a C, I will say. C means contour. Contour means any kind of path. Okay. It can be straight line, it can be some parabola, it can be any kind of shaped curve. So C is general name for curve or contour. So the integral has to be performed on the curve. And what is that you want to integrate is E dot dl, and E being a vector quantity, and what is the meaning is clear, that E is the electric field generated by plus Q. So because there is a charge here, that will generate an electric field, and therefore you have an electric field vector. dl is the path. So the contour C should be provided to you. So let us now draw what is the contour given in the question paper. So it is like this. You take a straight line joining these 2 points. If you consider a straight line joining these 2 points, then that will be a C. I will write down that this is your C. So we say that this is the contour. Either you can say that it is a contour or it can be a curve. So remember that straight line is also curve. Okay. A straight line is a special type of curve. It need not be curve means you should not think that there should be always a curvature. It's not compulsory. So straight line is the simplest form of a curve. So along this straight line, the meaning of this there, along this straight line, which means that the line is present, you have an arrow here because DL is there. So here you have a DL and C being the contour is given. That means C is the curve starting from P1 and ending at P2. And that's all. So this is the question. The question is evaluate the integral over the contour C of the quantity E dot dl, where the capital E is the electric field generated by a charge plus Q located at the origin, and C is given by a straight line joining the point P1 and P2 as shown in the figure. And that's all. That's the question. So there are two things are there. First, sometimes it appears to be a simple problem. There is the first thing. And if you think a little bit, if you want to solve, then you will be realizing whether any difficulty is present or not. So first of all, before starting this problem, first of all, you need to know what is the nature of the electric field here. Because first of all, you need this quantity. This E is generated by the Q that is present in the system. So in our problem, only 1 plus Q is available, and that is going to generate the electric field. So if you want to change the problem, then you can change this particular structure of Q. You can have multiple charges that will generate another complicated electric field. So like this, you can keep on changing, the variety of questions can be created. But this is the simplest situation where only one charge is there and that is going to generate the electric field. And then DL is, the meaning of DL is any small element. So let me show in this diagram. So if you are going to consider any small length, so in yellow color I am going to show that can be a DL. So DL will represent any kind of small length DL vector in this direction. So that is a differential length, it's a small length. And then by doing the integration, you will be making the entire length from P1 to P2. So that's clear. So before starting anything, first of all, we need what is the expression for the electric field. Then only we can perform the line integration. So therefore, we will write down that. So let me write down that this is the solution. Let me write down here. The electric field, let me say that this is the E vector, electric field at a distance r. So you know what is the meaning. This kind of, the style of writing, electric field is a vector quantity. It is a function of the distance, but distance is also a vector quantity. Therefore, you have E of r, and that is equal to, because it's a single point charge, the expression is simple. There is nothing to calculate further. If you have multiple charges, you may have to use the superposition principle, etc. So in this case, you have only one charge. Therefore, the expression for the electric field is straightforward. So we can write down the expression like this: 1 divided by 4 pi epsilon 0 into you have the Q is the charge that is present in the system, divided by, because at a distance r they have written here, so I have to use the same r here. So it is r square and then unit vector r cap, and this will be the electric field generated by a charge Q as shown in the diagram. So you have a diagram which is here anyway. So you have the copy of the diagram in your notebook. So as I am explaining, you are also writing down, and therefore, so even though I am erasing something, or if I am moving the board, you will be having a copy of that. So the expression for the electric field is fine, that is okay, but there is something which is very important. Now, what is important is the following. If you want to calculate a vector dot b vector, what is required is you have a modulus of the a vector, modulus of the b vector, multiplied by you have a cos theta, which means, what is the meaning of this is that you need an angle between the two vectors. So because the theta is coming into picture, you need angle between them. So right now what is required, since we are interested in evaluating the E dot dl here, we need the angle between the electric vector or electric field vector and the dl vector. And dl vector is there here in the diagram. So from here to here. So this vector will as you move along, for example, if you are standing here, this is the vector. If you are coming to this point, again, this is the direction. So because this is a straight line path, the direction will not change. So you are going to continue the same direction like this. Therefore, you have a dl direction. Dl vector has a specific direction. But the more important point to be noted is what is the direction of the electric field. Only when you have the direction, only when you show what is the direction of E, then you can find out what is the angle between them. So therefore, in the diagram, you have to show what is the direction of the electric field. And for that, you should know how to draw the electric field corresponding to a single charge, which is a positive charge. So you know that how to draw this. So basically, the electric field will be spherically symmetric. That means it will be like this. You draw anything in this particular way, that means it is supposed to be along the circle. So if you are going to consider a circle and then everywhere around the circle you are going to draw a radius. So it will be looking like this. So this is a symmetric field. So this is the direction of the electric field of a point charge. So, and the direction will be like this. So at any point, the direction of the electric field will be pointing outward radius. Outward radius means this is the outward radius. Let me show you what do you mean by outward radius. If you have a circle, let me draw here. Then if you are going to say that this is the radius, that's fine. So radius doesn't say anything about the direction. How do you say that it is outward or inward? There is no direction. Simply it is a line saying that from here to here is the radius is r. So inward, outward, that you have to bring, the concept you have to bring now, in the sense that outward means in the increasing direction of radius. So this is my radius r1. How will you increase the value of r1? I have to travel like this. So if I travel like this, then I get a larger radius r2, and therefore I will be able to draw a bigger circle here. So that will be you can draw a bigger circle like this, around this. So therefore r2 is a larger radius. So in order to achieve the larger radius, in which direction you have traveled? So in this direction you are traveling. Right? So I am showing the arrow here. So therefore we say that this particular arrow that is written is known as the outward radius. Radius actually doesn't have any direction. Radius is only a numerical number. How many centimeter is the circle's radius? The outward and inward, you bring the concept in order to deal with some vectors. So how did you bring the concept of outward is, you ask the question, how will you increase the radius of the circle? You have to travel in a particular direction so that I will increase the size of the circle. So that is called the outward direction. Inward direction means in which direction you have to travel so that the radius of the circle will reduce. So you have to put the opposite side. So it is clear that when you are going to have a straight line like this, and if you have a plus q here, if you draw an outward radius means this direction is the outward radius direction. That is what is the meaning. And if you are going to have a negative charge here, and similar electric field will be there here, and then you draw the inward radius like this. So the concept of the inward radius and outward radius is basically obtained based on this concept. So for a positive charge, there is a positive charge, you have to draw the outward radius direction. If you have a negative charge like this, you have to draw the direction of the electric field inward. That is the meaning. So that is the terminology that we are going to use, and that is what I have tried to explain here, that the electric field direction is shown like this, in this direction, and this is true for every line. For every line this is true, and you'll have to draw like this. That looks simple, but now only the problem comes. What is the problem is, once this is clear, what you understand is the direction of the electric field is not the same. You see here, at this particular point, I am now standing here. You follow the green color cursor. When I am standing here, the direction of the electric field is shown by this arrow. And now when I come and stand here, when I am going to come and stand here, the direction is this one. So this is the direction. That means the previous direction is different. The present direction is different. Suppose I will come and stand here. I will stand here. What is the direction of electric field? Means this is the direction of electric field. So therefore, the moment you change your position, that means if you move your location, the direction of the electric field changes. Now, why this is important? This is very important because you have to extend this particular line. This line has to be extended until this touches this particular line. You are going to travel from P1 to P2. Okay, so you are going to travel from P1 to P2. You are going to walk along this line. When you are going to walk along this line, what is happening to the electric field direction? Whether the electric field direction is constant or that the direction is also changing. That is what you have to think. So for that you draw the line here. So if I am going to draw a line like this, so that will be the direction of the electric field. So if I am going to stand here, see if you are going to stand here, the direction of the electric field is this. And in which direction you are traveling? Your travel direction is this. So I am now showing here in the pink color. The direction of your travel is this one, which is shown in the pink color. And then the direction of the electric field is shown in the orange color. So the direction of the electric field is shown in the orange color, this particular direction, and pink color will represent the direction of your travel. And now we are interested in this angle. So that is the angle which we are talking about, because it's an angle. Let me draw theta here. So this is what we are talking here. So the angle between E dot dl, this theta will keep on changing. It will keep on changing because you see here that if I am going to continue to draw this diagram for the electric field vector, then this is the direction of the electric field. Then the direction in which you are going to walk will be, that is the direction. And therefore this angle will be the new theta that you have. So this is the new theta. So this is a old theta. So theta value will change. It is not constant value. Theta is not constant, because you can very easily see that when you are going to start your walking, this is the direction of the electric field. This is the direction of electric field. And this is the direction of your travel. So as you can see that this angle is approximately 90 degree. Approximately, this is not 90, but at least you can see that something like 90 degrees is there here. But when you are coming here, theta is certainly not at all 90. And when you come to new theta here, certainly it is a much larger angle. So your observation from this diagram clearly tells you that evaluation of the E dot dl is not easy, because this particular theta is keep on changing as you walk. If I have all numerical values of the theta, then it is fine. You can always substitute that and then get the expression. But however, how will you get this? How will you get this value without having geometrical apparatus? You don't have. You are not going to draw an appropriate, exact geometrical diagram. You are not going to draw. You don't have a protractor to measure the angle and etc. In this particular situation, how will you evaluate E dot dl without knowing the angle theta? Okay, so initially the problem might have looked, or you may be feeling that the integral of E dot dl was simple. But once you think about how to evaluate the integral E dot dl, now you feel that there is some difficulty because the angle is changing continuously. So it appears to be a simple problem. Initially, it appeared to be a simple problem because the contour given is a straight line path. So you think that evaluation along the straight line is always simple, isn't it? That is the general opinion. Evaluation along a straight line is simple. Evaluation of the integral along some curved path may be difficult. So that will be a general opinion, but it is not true. So now you understand that the evaluation of the integral along the straight line appears to be somewhat complicated. So now you are going to use some idea here in order to solve the problem. But let me tell you that the problem is not difficult. It is a quite simple one. But for that you are going to use some idea now. The concept that we are going to use to solve the problem is, so we are going to make use of a fact that the electric field is conservative. So we are going to make use of this particular feature, or because this electric field is having this interesting property, the solution of this problem is going to be simple. That is exactly what I am going to demonstrate. So what is the idea here is that the meaning of the electric field being conservative, the meaning is, what is the practical meaning? The meaning is like this, that the evaluation of the integral, let me write down like this. So the evaluation of the integral is independent of the path, independent of the path of integration. So that means when you have a point P1 here and another point P2 here, and the original question paper says that you evaluate along the straight line. That is what original question paper says. But now what we are going to do is, we are going to reject that idea that let us not evaluate the integral along the straight line. We are going to reject that. Instead of that, we will choose some other path. Which path you are going to choose? Okay, that freedom is there up to you. You can choose any path. For example, I may be choosing a path like this. So I am now choosing a path like this. So this is the original one that is given. Given is that you travel along this straight line path. But I am not going to travel along a straight line. So I am going to choose this. For example, I am now drawing another option actually. So I may be planning to choose this particular path to reach P2 here. So P1 to P2 can be reached by different path, and that is what is the path which I am writing. Independent of means whether you are going to choose this kind of a complicated path or whether you are going to choose a simple straight line path, it does not matter. That does not matter is the independent. It does not matter, but finally you will get the same answer for the integration. That is the meaning of this. Evaluation of the integral is independent of the path of integration, means that our integration of the E dot dl, whether you are going to choose the original line that is given in the question paper, or that I am going to choose some other curve I am going to choose, and along that particular curve which I am going to choose, I will evaluate the E dot dl. Then interestingly, what happens is that these two integral become identically same value numerically. If you evaluate this, you will get the same answer, and that is what is the meaning of conservative. So the meaning of the conservative can be explained using a line integral like this. This is how you understand the conservative principle in terms of mathematics. In terms of physics, how do you understand conservative? Conservative is something that doesn't change. It possesses its original value. That is how you understand the conservative. How, as an example, I will tell you. For example, if you are, let us say that your monthly salary is 45,000 rupees per month. That's your monthly salary. And let us assume that on the first of the month, okay, assume that this is the first of the October, and you get 45,000 rupees as your salary. And what happens is day by day, okay, every day is going, and then you reach 31st of October. That is, okay, whatever it is, last day of a month. You came to the last day of the month, and then you are now finding, or you are checking how much money is left out with you. And if you surprisingly see that again same 45,000 rupees is there with you, that means we say that it is conservative. You are conserving the money. In the sense, what do you understand in that particular way is that whatever money that you get is retained with you. You are not going to spend. That is, even without spending any money, you can survive. Okay, that is the meaning. So whatever is given to you, it will be retained by you without wasting. That wastage is what is important. The word conservative is connected with the wastage. Wastage can be in any form. In the case of the physics, non-conservative means wasting happens in the form of heat. If you are going to do a friction, if some object is moving, then there will be some sliding friction will be there. So that friction, what happens actually is that the energy is converted to heat. Energy is there still, but it is in the form of heat. But in mechanics, we want mechanical energy, not heat energy. So therefore, whenever this kind of heat is happening in the mechanics problem, we say that conservation is lost. So that is how you understand in physics. So electric field is conserved here in this particular electromagnetism. It means that your integral E dot dl, this is what we are going to give the name. Already you know what is the name. we have seen in the last 2-3 classes. We have given the name called the potential, and we are going to say that this potential is going to retain its value. It's going to retain its value irrespective of whichever path you are going to choose. So that is, the potential doesn't change because you are going to change the path. Okay, because this is something which is something you have to think carefully, because when you are going to change the path like this is the straight line path that you have, this is a curved path that you have. If you are going to think about in terms of some daily life, then this will not happen. What is not happening, you see, suppose you travel along the straight line, you take a two-wheeler and then travel along the straight line, 10 kilometer you travel, you reach point P2. Then you come to choose this, then you take the same two-wheeler and then start from P1 and come in this direction. Now, certainly you know that it cannot be 10 kilometer. Straight line path was 10 kilometer, but this may be much longer distance. Let us assume that this is 17 kilometer. So you traveled 17 kilometer and then reached the point P2. So very clearly, you know that you have already spent a lot of petrol to reach that. What is the meaning? The meaning is the total money spent from point P1 to point P2 using straight line is less. You spend less money and reach the point P2. If you are going to choose this path, then you have to spend more money. So less money, more money means this equality will not be there. So that is what we mean to say. From the daily life experience, this is contrasting to you. Okay, this the properties, we say that it is important because irrespective of whichever path that you are going to choose, the value of the integral is going to be identically same. That means you travel along any path, you will be spending the same amount of money in terms of electrostatics. Money means not exactly money, the value of the integral, and in the meaning of the money in electrostatics is this potential. That is what you have to understand. So the potential difference between the point P1 and P2 will not change, whatever path that you are going to choose. So that is the physical understanding of the word conservative here, and we are going to make use of this interesting property to evaluate our original problem. So you should not forget what is our statement of the problem, that our today's aim is to solve this particular problem, that we have electric field like this because of the positive charge plus Q, and we are interested to travel from P1 to P2. Originally in the question paper it is given that you have to travel by straight line, but now you are making a statement that we are going to reject the option of traveling in the straight line and we will choose our own path. Our own path we will choose because of the reason that any path can be chosen, we will get the same answer. For that reason we are going to choose. So to that much is clear now. Then comes the question, if you are going to choose your own path, what is the path? So which path are you going to draw and how are you going to travel? So that is what is the next step. If you can identify which path that you are going to choose, then we are almost done. Almost your problem is solved. So we are coming to the next stage. So which path are you going to choose? So you have to decide which path. So for that, what you do is you again bring some idea here. The idea is that if you want to calculate A dot B, for example, then interestingly, sometimes this becomes 0. When it will become 0? When the A vector is perpendicular to B vector. So this is the first idea that you get from mathematics. There is a second idea is there. Second idea is that A dot B will become simple AB. AB means A multiplied by B. Both of them are magnitude of the vector. Cos theta disappears. Why cos theta disappear means not disappearing. It is actually cos theta equal to 1. So basically AB into 1. When cos theta will become 1? Cos theta will become 1 when theta equal to 0. What is the meaning of theta equal to 0? That means the A vector and the B vector should be parallel. So I can write down that when A vector is parallel to B vector. These two things is your idea now. This is what is your idea. Now why it is an idea here is that there is an interesting thing happening here. The interesting thing is that the A dot B becomes 0. So therefore when something becomes 0, then you don't have to evaluate, right? So why do you want to evaluate all complicated integral? Finally it is going to become 0. Like that you can say. but this will happen only if, okay, only if A perpendicular to B. So this is one place where your integral becomes simple. Okay, you can escape from evaluating the integral and put it 0. So this is one idea. The second idea is that A dot B is equal to A into B. But what is the advantage of this particular expression is theta is, you don't require theta. You see, in this expression, you don't require theta. So you don't require theta. That is why this particular equation is a simple equation. This particular equation is simple because forget about requiring theta. The answer itself is 0 here. So because this is 0, this is much more simple. So therefore, evaluation of the A dot B happens to be simple under two special conditions. One condition is A perpendicular to B. Second condition is A parallel to B. Now in our problem, what are we going to evaluate? We want to evaluate integral of the E dot dl. Forget about integral. First we will discuss about E dot dl. So therefore you ask the question, do you have any situation like E perpendicular to dl? Do you have any situation? You have to ask. And also ask, do you have any situation where E is parallel to dl? If anything, option 1, this is your option 1 and this will be your second option. If option 1 and option 2 is going to happen along your path, then that path you will be choosing. This is the idea. So which path? This is the idea. The question is clear. Which path you want to choose? That is the question. Answer is here. I am going to choose some particular path such that I will either satisfy E perpendicular to dl or E parallel to dl will be satisfied. One of these conditions will be satisfied. If it is satisfied, then the answer can be easily written down that you can write either 0 or you simply write AB. So I don't require theta, because this theta only created a problem for you, right? So let us go back here. And I told that this 90 degree is becoming something else and then it is becoming new theta, and we do not know without having this theta how to calculate. That is how you started with the difficulty. Now those difficulties will be completely removed, and that is the idea. So completely you got what is to be done now. Now discover some path here so that you either choose a perpendicular condition or you choose a parallel condition. So that is what is the idea, and I will now draw the diagram corresponding to our understanding. So let me again draw this. So you have a positive charge here, and you have somewhere you have a P1, for example, some P1 is there, and then let us say that is your P2. How to draw this? So that is the idea. So let us draw now. So first what we will do is we will draw a straight line from Q. So this is actually your charge Q. So that's what is written here, and then you got it. The second thing is, so that's over. Now what I will do is I will try to draw a circle around this. Okay, let me draw a circle. So what I have done is, you have a charge here. This is our original point P1, which is x1, y1, z1. Okay, I will avoid x1, y1, z1, and then I will write down instead of that an r1 vector, because that is equivalent to x1, y1, z1. So basically I have drawn a circular path for visuality. Okay, I'm not going to travel along the circle, but I just want to draw a circular path around this particular thing, which means that the radius is r1. So the purpose of drawing this is to understand that this r1 will come here, because once you draw a circle like this and this being the center, you can see that this is the radius of the circle r1. So to have the visualization, okay, your mind will register that distance will be r1 only if you have a circular path there. So that is why I have drawn a circle. And similarly, we will also draw another circle from Q being the center to the point P2. So I have drawn a circular path. You don't require a full circle. The circular path is required in order to make some visual feeling of the distances. As you see that this being the r1 being the distance from the charge Q, you can also understand what should be the distance of this point from the Q. Now because I am drawing a circle like this, and P2 is the position x2, y2, z2, and which is nothing but an r2 you can write down. And therefore, if you are going to choose from here to here a straight line, then that distance should be R2. So let me draw a straight line, and that's it. So that distance should be in R2 here. So I'll write down that this is R2. R2 is measured from this particular origin, and this should be in R1. So R1 and R2 is visible now because of the circular path. See, in the earlier diagram, you have an earlier diagram here. Of course, let me go back here. This is also same diagram actually. There is a P1 here, there is a P2, and basically this X1, Y1, Z1 is your R1, and X2, Y2, Z2 is your R2. So that is clear, but you don't feel any radius coming into picture. Okay, you will get a feeling of the radius if you have some circular structure is there. So that is why I have drawn it, and then it is possible to have a feeling that you can have a distances R1 and R2 is now visible. This is first point. Second point is that I'm going to that which path that you are going to choose. So that is our question. So the answer we'll see. The answer is that we will be choosing a path such that the E dot dl will be either parallel or perpendicular. So let us choose which one will be a parallel one. The parallel one is very easy, right? See, this is the direction of travel. Suppose if I'm going to travel, you follow the green color cursor. Okay, so I'm going to travel like this. If you are going to travel like this, then this is the direction. So this is the direction of what? This is the direction of R2 because this is the radius. So if I'm going to start here and if I'm going to travel like this, that means basically I'm traveling along the radius. That means this is the direction of dl. Dl is, this is the direction. What is the direction of the electric field? Direction of the electric field is identically same as the same line. How do you know that? Because that structure you already know. You see here, this particular line, wherever you have, for everywhere you will have to draw the radially outward direction. So that will be the direction of the electric field. So therefore, interestingly, what happens is, if you want to travel, if you are going to choose this particular pink color line as your travel path, then that also happens to be identically same as the electric field vector direction. And therefore, now you are achieving a condition that the electric field is parallel to your travel path. So is this point clear? And therefore, I will make it as a path now. And let me draw a continuous straight line so that you are going to travel along that line. Okay, so in blue color line, I am now showing that it is now clear that I am planning to travel like this. So the direction also I am showing. So this is the direction in which I am planning to travel. That means my dl vector will be in this direction. That is, all the arrows are there here. And what about the direction of the electric field? Electric field direction is also identically same. So I am showing the electric field direction, that is this blue color line. I am showing the direction of the dl, that is also identically same. And therefore, along the blue color line, I will write down that along the blue color line, the E vector is parallel to dl vector. So I am achieving this particular condition. Therefore, I will be traveling like this. Now but however, what happened is I am able to travel from P2 to here, but I want to reach P1 because the integration is given as P1 to P2, isn't it? So I want to do the integration from the point P1 to the point P2 E dot dl. This is what I have to evaluate. The original problem is this one. So therefore, P2 I know that I can reach P2 now, but however I am standing here. So P1 also I have to cover, then only P1 to P2 will come. So naturally, you can think that the path along the curvature, that is an arc of a circle, if you are going to travel like that, then something interesting happens. So that is what we are going to choose. So let me choose another path as the arc of the circle. So let me make that as a continuous line instead of the dashed line. And that's all. So the one which is shown in the orange color, so that will tell you the direction of path. That means I am going to travel along this direction. Therefore, the dl vector is shown in this orange color orange color arrow in this direction. So dl is clear. Then what about electric field? Electric field vector is very clear that everything will be directed radially outward. So if I am going to draw, because we don't want this vector, I will show in a dotted way what is the direction of the electric field. So the direction of the electric field will be drawn always along the radiuses. So this is one radius, this is one radius. So like this only you will be drawing the electric field direction. So therefore, these are all the possible directions of the electric field whenever you reach that particular point. That particular point means this one. So this particular place where I am showing the green color cursor, for that place, this is the direction of electric field. And for this place, if I am going to stand here, this is the direction of the electric field. So what do you understand from here? You understand that the direction of the electric field and the direction of the DL are perpendicular. So that conclusion I can write down that DL is perpendicular to the electric field along every point along the orange color path. That's why I'm writing this particular condition. What I have drawn in the orange color is satisfied on every point that you stand along this line. It is true. Similarly, once you reach this blue color line and anywhere you stand along the blue color line, this condition is satisfied, parallel is satisfied. So finally what happened? Did you achieve anything or not? So I am going to start from P1. This is my starting place. I will travel along the yellow color line, come at this particular point, and then I will start my travel along the blue color line and then reach my point P2. That means I will start from P1, I will end at P2. This integral I have to evaluate. That's all. So now this diagram clearly tells you that my integration will be done on a contour. Contour means a path which consists of two different styles of what is called a path. One is the curved path and the another one is the straight line path, and they are shown in the figure. Okay, the one is the orange and the other is the blue. And how do you write it mathematically? And we now write down finally that our integral of the E dot dl, we write like this. Integral of E dot dl is given by, where C is the contour, is given by the integral along the orange color line. I will say that orange curve, for example, of the E dot dl plus the integral over the blue color straight line of the E dot dl. So there is nothing wrong in writing. This kind of writing is there is nothing problem. You can always write like this. And if you don't want to write this, then you can give some name. Okay. So for the time being, since we have not given any name, you can always write down what is the name of the curve that you are going to follow. But for that, you should have a diagram like this. So once the diagram is clear, you can always write like this. So our integral is therefore split up into two integrals. The one integration along the orange curve and the second integration along the blue curve, and then you add up them, then you will be getting the integral P1 to P2. And that is exactly what we are going to do. And once this is clear, the calculation is only very simple, and we will be getting probably in 2-3 steps. And that's all. The problem is almost over. Now let us see what it is. And before going to anything else, let me tell you that this integral is 0. So that is why I told that now the problem is simple. So this is equal to 0. You don't have to do anything because E vector is perpendicular to the dl vector. The integration along the orange color curve will be 0. So that means your one integration is over. Only one integration is now left out. You have to start the integration from this particular point, which is a white color dot I am keeping, to the point P2, which is another white color dot I am keeping. So white color dot to white color dot, you have to perform the integration, and that is your second integration, namely the blue color curve. That is what we are going to do now. And let us go down here. So let me write down that the required integral P1 to P2 of the expression E dot dl is given by the integral over arc. So instead of using the orange curve, blue color curve, etc., we will use some little bit of technical word. It is an arc of a circle. Okay, so it is an arc of a circle. Then we will write down that this is integral E dot dl plus the integral over L being the line that we are going to represent. Maybe you can show that as a L here, and then I will write down that this is integral E dot dl, and that's all about it. And that is equal to 0 plus integral, because just now I explained that if you are traveling along the arc of the circle, because of the perpendicular nature, this is 0, and then integral over line, and here you have to go back and put the appropriate limits here. So what is the starting point? This particular point is R1. How do you know that it is R1? It is there here. So you go like this and then come here, and there is an R1 here. Therefore, Therefore, this particular point is a distance r1 from the charge q. So that is why the circular path will help you to visualize what are the distances. That is why I have drawn the circular path. Otherwise, this full circular path is not at all required. This will enable you to get the idea that the particular point, the white color dot that is there here, will be the point r1. And what about the another white color dot here? This point is r2. That is written here. So this is an r2 here. And then there is an r1 here. Therefore, from here to here means r1 to r2. So basically, ultimately what happens is that this integral over the line L is written as r1 to r2. Then you have E dot dl. And that's all. So because the first term is 0, it is only a matter of evaluating the second term, and that we can write down like this. So that is equal to, so integral r1 to r2. Let us write down the vector expression for the electric field. And what is the vector expression for the electric field? So that is the expression for the electric field. Dot dl vector is, this is the magnitude of the dl multiplied by the unit vector. Because this is clear, right? So when you are going to travel like this, a particular line like this, if you travel like this unit vector is r cap, that is the direction. Electric field is also in the same direction. Same direction is the electric field. So therefore, electric field unit vector will also be r cap. Both of them are r cap. So this is your small distance of your travel. This particular distance is your dl. So for the dl magnitude, the unit vector is also r cap. So because of that, we have written like this. And once you have this, we can now say that r cap dot r cap will become 1. So your vector has disappeared, and then you have only the dl. And remember that the dl is going to be dr in our problem. So I will make a small correction here. L is okay, generic name, but because we are using r here, the small length should be r. So if the total distance is r, then the small length should be dr. That is a good idea, right? Okay, dl is generally, we can say length is dl. So now we need a appropriate symbol. So dr is a better symbol than dl. So therefore, I will make this as a dr. So that is equal to 1 divided by 4 pi epsilon 0 into, so q is also constant. So let me take it outside the integration. Then you have an integral, you have dr by r square, and it is from r1 to r2. So that gives you q divided by 4 pi epsilon 0 into, the integral is actually minus 1 by r. So minus 1 by r, if I substitute, I will be getting 1 by r1 minus 1 by r2. So this is your required integration, integral over c E dot dl. So once you finish this, the important conclusion that you are going to make is important. What is the conclusion is, this is the integration right side. The right side value that we obtained is along the contour that we have chosen. But however, at the end of the day, you are going to say that whatever answer that I got here will be exactly the same if I have made the integration over the straight line that was given in the original question paper. That is what is the statement you are going to make. Even though I did not evaluate the integration along this straight line given in the original question, I will be getting the same answer. Same answer means whatever you got here. So whatever you got it here, for example, the same answer what is there here, I will be getting if I am going to do the integration along that particular straight line. But actually, how did you got it? Actually, I got it based on my own path. Okay, so this is the conclusion, and therefore in this problem solving, you have made use of an important feature, namely the path independence. Because the integration path is independent of whichever path you are going to choose, I have made use of that freedom. Okay, you enjoyed that freedom, and then you yourself chosen any path as you like. And this is where the thinking power comes. One has to think what kind of alternate path that can be used in order to do the integration. So the original question paper, they will give you one particular contour, but however that contour may appear to be difficult. Ultimately you choose your own contour such that the integral becomes easy. That's exactly what we have done. So ultimately this is the answer now. So but however we will make some conclusions. There are some important conclusion from this particular expression. So now we got this. So we started with a problem, we got the answer, that is fine, but that is not our only interesting aim. The solution of this particular problem is also useful to understand some other foundations, or some more understanding of the value of the integral E dot dl, and that's what we have written. There is an important conclusion that can be drawn from this equation. What is that you are going to draw is that, suppose if you are going to choose, if you are going to choose that R2 approaching infinity, if R2 is taken to be infinity, then what happens, you see that if it is so, then the integral over the contour, any contour, now that you understood that the contour can be anything, whatever contour that you are going to choose, you will be getting the same answer. So therefore you don't have to worry which is the contour that is to be considered. So integral over the contour, then you have an E dot dl will be equal to, so R2 you substitute as infinity, so I will be getting 1 over infinity is 0, then you will be getting only this expression, that we will write it as 1 divided by 4 pi epsilon 0 into q divided by R1. So R1 will be, is the only one radius that is there. So whenever only one radius is there, R1 is not required. The suffix 1 itself can be deleted and you can simply say that it is R, isn't it? So when two R's are there, you can say R1 and R2. Now you have only one R, therefore this can be also written as 1 divided by 4 pi epsilon 0 into q by R. And this quantity, this one, we are going to call, we will call this the electric potential. So that is only a name, that's simply the name that you give. Okay, so whatever expression that you got, you simply give the name saying that this is the electric potential, because discussing things in terms of this expression sometimes is much more convenient than otherwise. So that is why we give a name like this and then keep this expression for the electric potential. Otherwise, every time you have to evaluate, you say that I am evaluating E dot dl, like that you have to say. Now you don't have to say that I am evaluating E dot dl. Okay, so that is why the advantage is that when you give the name, we will be using frequently. That is why. And there is some more point that has to be noted here. What is that you are going to notice that this expression that you obtained, generally whatever you have done from the beginning to the till now, is for a positive charge. So remember that we have chosen a positive charge. Okay, for negative charge anyway, the appropriately you'll have to put a minuses and then there may be some reversal of the sign here. So that's why that confusion should not come. The discussion that we have made is that we have considered a plus q charge. That is the first point under condition. So this is the first thing. So the second thing is, the second point is that your R1, the R1 is less than R2. So anyway, that is clear, you should be remembering, otherwise I'll just go back here and so. So this is the R1. R1 is a smaller radius. R2, this is the R2. The pink color circle is a larger radius. So this is small radius to bigger radius. If these things are valid, or if you are going to maintain these things 1 and 2, then only this expression comes. If you are going to reverse the size of the circle, for example, or if you are going to change the plus q to minus q, then this there will be a change of signs. Okay, all the pluses will come to minus, minus will become plus. So that is why I want to make sure that certain things are important in understanding these things. So when you are going to define, so I have written that when we will call this the electric potential. What do you mean by this here? That is why I want to tell. This means when we are going to consider a positive charge in our definitions like this, under that condition, then this expression will be called electric potential. Otherwise, a minus will be floating here and there. Then you get a confusion. Why minus is there in some equation? Why it is not there in some other equation? Okay, so this is the important point that I want to tell you. But however, let us make a clear conclusion from this. Here I have written that the integral R2 is tending to infinity. So where it should be written in the integral? In the integral you have not written. Remember that this actually practically you have done an integration from R1 to R2. Okay, even though C is any contour, ultimately what happened? We have chosen a contour such that finally R1 to R2 only is surviving. The other integral is 0. You see here, that's what it is. See, R1 to R2 only finally it is coming. The other integral is 0. So only R1 to R2 is only surviving, and that is the only thing giving you the answer. And therefore, the integral over C is actually nothing but integral over R1 to R2. So that point I will make it clear and then write down that this is integral E dot dl. And once this understanding is clear, and if you are asking the question or if you are discussing the condition of R2 going to infinity, that infinity has to be transferred here. And therefore, I will write this expression as integral R1 to infinity, because R2 is infinity, that is what is written here. And then I will write down the same E dot dl. So our conclusion is, so that's what I'm making a conclusion, that if you are going to choose R2 as infinity, then the integral is essentially R1 to infinity of the quantity E dot dl. And if you simplify all these things, ultimately what expression I am getting is 1 divided by 4 pi epsilon 0 into q by r. And there is an r here. You remember that the r means this r1. Okay, r1 and rr both are same. So therefore, in order to avoid that the additional suffix 1 is not at all required, and therefore this 1 can be deleted. I'll delete this. Okay, so I am actually deleting this suffix r. I mean the suffix 1 I am deleting because it's not required. R1 is basically r because only one radius is there. So therefore here also I will remove the suffix. So we have the conclusion now. Let me write down the conclusion. This board I will move a little bit. So finally what do you have? So finally what I have is integral r to infinity of the quantity E dot dl is equal to 1 divided by 4 pi epsilon 0 into q by r. This is what I have ultimately. And once again, just to refresh your memory, q has to be a positive charge. This is the first condition you have to remember. R will be a smaller radius, so that this must be automatically infinity will be a larger radius. So only thing is that q should be positive. That is important. If you are going to put a negative charge here, then one minus will come into picture, and that will give you confusion. So we are going to make this as a definition. So when we are making some definition, things should be made clear. Okay, suddenly a minus should not come, or the minus should disappear. Something like this should not happen. So that is why I am making the things a little bit more clear by explaining or repeating certain things. So what we'll do is we will make use of the property of the definite integral, that you can interchange the limits. This is the lower limit and this is the upper limit. The upper limit and the lower limit can be flipped. Flipped means you can interchange. But however, the value of the integral will not be changed if you attach a minus sign. So therefore, I will put a minus of the integral. So I am attaching a minus sign here. Now to compensate that minus, I will flip the limits. So flipping the limit means put the upper integral to the, put the upper limit to the lower limit and put this r as an upper limit. So that change will be compensated by a minus here. So therefore, these two are identically same. Then I can write the integral E dot dl will be equal to, this quantity is the same thing. Let us say that 1 divided by 4 pi epsilon 0 into q by r. Nothing happens to the right hand side. Only in the left hand side, we have rewritten in such a way that infinity comes to the lower limit. That's all we have done. And for that, we have attached a minus sign. And this expression is what we are going to say that it is a definition for the electric potential. So that is why I am making it clear So this is the equation used as definition of electric potential. And let us write down another final form, that minus integral infinity to r E dot dl. Now instead of writing 1 divided by 4 by all these things, since we are going to say that this is electric potential, the symbol for the electric potential is V. Therefore, let it be V. And the electric potential will be a function of R, because R is there here. Therefore, it is a function of R, but only magnitude is enough. So let me put a box here. So this is the final definition that we are going to use. So even though we started with a way of solving a particular problem, finally what happened is that solving a particular problem also enables to understand some basic defining equations. So this will be the defining equation for the electric potential. So these two are same. So you can also say that this is also the defining equation. Only thing is, here you have the exact expression for the point charge. Here this is a general expression. So this is the definition of the electric potential, not necessarily for a point charge. That is the difference. Here you made a very small change, but however the meaning should be clear. The previous equation 1 divided by 4 pi epsilon naught into q by r is valid only for point charge, because that is what you have been doing from the beginning of the today's class. But what we are going to say in the next step is, that is the one which is put a box here. What we are trying to say is, this is not only true for a point charge. This is true for any collection of charges. So even if you have a distribution of charges, if you have many charges which are scattered around, then that particular electric field will be E, and the corresponding electric potential will be V. Even then, this particular definition is valid. The expression may not be valid. You won't get the same expression if you are having 25 charges. For 25 charges, you won't get 1 by 4 pi epsilon naught into q by r. That you won't get. But however, there will be an electric potential, and that is the written by V. And the E will be corresponding to that electric field. So the statement written in the last line and put a box here represents that the meaning of this equation is valid not only for the point charge, but for any kind of charge distribution, in particular discrete distribution. Okay, anyway, it is valid for continuous distribution, that we will see later. So our conclusion, therefore, you should appreciate that even though we started with a simple problem, it gives us an important conclusion, and this happens to be a basic defining equation. And in this, you note down that the definition starts with a minus. So minus integral infinity to r of E dot dl is known as the electric potential. And in that definition, underlying assumption is the electric field is the one generated by a positive charge. That is important. If it is not a positive charge, then this minus will not be there. So that is why these two things should be going together. Only if the electric field is generated by a positive charge there, you will get a minus is attached here. If it is negative charge, what will happen means automatically if you simplify, negative will disappear. Okay, so that is the point that you have to remember. Okay, with this we will stop, and the next class we will take up another problem of this type, or we will discuss more about the electric potential. So that we will do in the next class.